The fall 2012 final exam had finished up with 4 multiple choice type concept questions, so I'm going to work through all those now. These were just 1 point apiece, so obviously they won't require any significant calculations. Number 13, we're given a wall with an area of 300 square feet, and we want the area of a 1/10 scale model of the wall. Key point here is that this is a linear scale. We've always given scales in terms of the linear values, so we're getting 10 times smaller. So the area is going to be 1/10 of the model. It's going to be 1/10 squared the area of the actual thing. Okay. So the area of the actual thing is 300, 1/10 squared is 100, so that's going to be 3, let's see, I'll write it this way, 1 over 100 times 300 squared is equal to 3 square feet. If it helps, you might envision an object of 300 square feet would be, let's say 30 times 10 will give us 300. So if we make a 1/10 scale model of it, it's going to be 3 by 1. Again, you can easily see that area is 3 square feet. Number 9, everybody's favorite type of problem, an airplane relative motion problem. So we're given some information here. The key point we want you to know is that the velocity of the plane with respect to the ground, this equation, as a vector, is equal to the velocity of the plane with respect to the air plus the velocity of the air with respect to the ground. So this is the wind. Okay, air with respect to the ground is the wind. This is usually called the airspeed. Okay, and this is called velocity with respect to the ground. So we're given 4 vector diagrams here. Let's figure out which vector's which. Needs to fly in a direction of 20 degrees east of north. So that gives us the direction of the velocity of the plane with respect to the ground. Okay, here's the magnitude of the velocity of the plane with respect to the air. So we said that was airspeed. And here is the velocity of the wind, or excuse me, air, is the way we wrote it, with respect to the ground, or the wind. Alright, so let's look at this vector first. The wind's blowing 70 miles an hour, 30 degrees east of north. Alright, so here I'll put it in red. It's obviously in all 4 diagrams, that's the wind vector. 30 degrees north of east would be this 60 degrees east of north, so that's the same in all of them. Okay, so that doesn't help us a whole lot. Let's look at this 20 degrees east of north. So 20 degrees east of north, this north is right here, it's going to be this 70 degree angle, so we're looking at this vector. I'll draw it in green. Okay. And make the arrows a little bit bigger. Let's see, so here it is. We get a little confusing here, but just to hopefully try and explain it. So the green vector is the 70 degrees east of north. The 20 degrees east of north, 7 degrees north of east. Okay, that's our velocity of the plane with respect to the ground. Okay, but here in this one, it's labeled with the magnitude of the plane with respect to the air, so that's not the right one. And this isn't the right one, because we've labeled the associated the wrong value of the speed with the direction. So we've eliminated those two. Okay. So I'll go ahead and label this as the velocity of the plane with respect to ground. We know that's correct in both of these. Okay, so let's look at our equation over here. We have plane with respect to the air added to the air with respect to ground. So vector addition, head to tail. Okay, and we're just already narrowed it down to these two. The 350 was the plane with respect to the air, and this we said was the air with respect to the ground. Alright, so over here this is the velocity of the plane with respect to the air. We don't know its direction. Okay, so this diagram right here, if we look at head to tail, these two vectors right here are head to tail. This actually represents the velocity of the plane with respect to the ground plus the velocity of the air with respect to the ground, and we're saying that is equal to the velocity of the plane with respect to the air. Okay, this is not true. Okay, this does not match that equation, so this one is wrong. And to check, this one is the plane with respect to the air plus the air with respect to the ground, adding those as vectors, is going to give us this resultant plane with respect to the ground. A lot of words there, but hopefully that will help some of you. Number 15, object subject to a force displacement curve is shown. Amount of work done on the object. Okay, so we had one equation, integral of f dx will give us work. Okay, so we are given a displacement force curve. The area would be that added to that, but since this is below the axis, it's negative. Okay, rectangle, this is 10 high, or negative 10 high, times 4 wide, so that's going to be a minus 40. And this one's 10 high times 4 wide, that's going to be a positive 40. So the total work is going to be the sum of those two areas is going to be big 0. Key point, force displacement gives you work. Force time, if we were to have had one of those, would actually give you impulse. Okay, last one relates to the last module we covered. Hopefully you remember the demonstration of the spinning bicycle wheel with some sort of axle right here and then hung by a rope. Okay, so we're supporting it in the vertical direction with a rope, and if you remember the demonstration, the bicycle wheel was spinning this way, and it actually started rotating about this vertical axis. So it's sort of not only rotating about its axis of the wheel, but it would rotate about this vertical axis and sort of come out of the paper and then back in and go around this way as the wheel was spinning rapidly. And the way we explain that is that there's actually an angular impulse. Okay, and that angular impulse, I think we used L sub A, was equal to the torque times cross product with the omega. Okay, so if we have a torque that results, so if we look at that point right there, the weight of the wheel is in this distance right here that I'm going to draw in red. Okay, so force times the perpendicular distance is going to give us a torque going around that way. Alright, and it's very hard to draw on this picture, but we do have an omega of the wheel, okay, as it's spinning around this way. Alright, so remember the torque direction. Again, it's going to be really hard to envision, and I don't really need to explain this for this question, but I'll finish up real quickly here. The torque is coming out of the screen, so imagine a vector actually going into the screen since it's clockwise. A vector going into the screen. Okay, the axis of omega, assuming it's spinning sort of this way. Okay, so imagine this, the wheel spinning that way. The axis of omega, let's make it the other way. We'll make it spinning downward here. Okay, so the axis of omega would actually be coming out. So we have our torque axis. I'm going to draw it with an X going into the paper. We have an omega axis coming out. Okay, so torque cross omega going in, cross this vector to the right, okay, would give us a vector pointing downward. So this is the axis that it's rotating about, that angular precession axis. Okay, again, rotating about this axis means it's sort of coming out of the paper, going back in around this axis we've labeled the vertical or z-axis. But again, this is the key concept. Angular impulse is change in angular momentum. And remember, angular momentum was torque and omega.